So whenever you're learning something very new, the first couple of days seem very easy, but they are so foundational. We're going to do a lot of definitions. Some of the definitions I'm going to whip through a little bit just to save some time because it's going to be long. But you got to remember that you have these definitions. You got to come back to them. I'm going to give you a few little tips along the way as well that are going to become more important in a few days, but like really important. There's a great opportunity to be very successful in these 2 units. In a lot of ways, they're quite easy compared to a lot of what we've done. However, people don't always do very well because they're busy with their other subjects. And because it's new notation, they don't take the time to get into the vectors mindset, right? So today we are saying goodbye entirely to calculus. It's gone. No more calculus until the final exam. And then it's all vectors from here on in. We do 2 units. We have one that's just on vectors and all the things you can do with vectors, and it can be quite different. And then the next one is on using vectors to do lines and planes, and some of it goes right back to grade 9. Straight lines come full circle for high school math. Grade 9 is all about straight lines, but it's a bit more eloquent. It's a bit more it's new notation, so it's a little bit trickier and it's a bit more powerful in some ways. And if you take linear algebra in university, this is sort of the start of linear algebra. We only touch on it, but there's a really great video series that explains the visual aspect of linear algebra. I will post it to the classroom, and you can watch it because it's interesting. But if you take linear algebra, I urge you to go watch it, because when I took it, I took it through all of university, and when I watched these videos 15 years later or whatever, I was like, I didn't know any of that. Nobody told me that. That would have been really helpful. So unfortunately, they don't always use the visual. Maybe that's changed. I don't know. But it's really interesting, and it's related to vectors and that kind of stuff. But the vectors that we do are similar and associated, but not quite the same as the way that video presents. At any rate, how many people have taken physics? So you've done vectors? Good. So you can help me out throughout this, because a lot of the definitions start off the same, but I will tell you what we end up doing throughout these 2 units is quite different from what you do in physics. So if you think you kind of know it all because of physics, we have a very different take on it. Okay. And there's some things that are very, very different from just all of the math that you've learned. You kind of have to throw some of your old beliefs out the window and start fresh. And it's interesting because learning a new number system or learning something new from foundation goes better if you can learn it slowly over time. I mean, how long has it been since you've been learning about numbers? Kindergarten. So 12, 13, 14 years. You have to learn all of this from foundation up about vectors in a couple of weeks. That's the challenge of this. Okay, so be aware of that. Doing the practice, all that kind of stuff is really going to be important. We're squeezing 2 days into one, so tomorrow will be only a work period. It's a 33-minute long period. I'll talk more about that after, but just so you know, that's why we're kind of going fast. This is 2 days worth of material. Then the first day, you're going to be like, we didn't even hardly do anything, which is true. Normally, we don't get a lot done on the first day because, again, it's just getting your mindset around what a vector is. So let's dive into this. Some definitions. What is a vector? This is the same as physics. A vector is a quantity that has a size which we call magnitude now. Okay. So that's a really important word. We'll use it constantly. But the difference is it also has direction. So somebody give me an example of a vector. I love it. Velocity, because you even named it. 5 meters per second. Did you say left? Great. What's another one? How about 8 kilometers north? This won't come up very much because we just don't do it a lot. We used to do it a little bit more. We don't do it as much anymore. But it might come up in your life. So because it's appropriate here, I like to talk about it. I could do something like this. I could do 30 kilometers and then north 30 degrees west. So this is a standard way of, this is one of the two standard ways of describing directions in like northeast, southwest. This one is either called quadrant bearing, or it has another name. I should write it down because it's a strange word and I don't know it. Quadrant bearing is all about the quadrants. So the way this works, you always start on the vertical, either north or south. And so I start north and I go 30 degrees to the west, obviously. With the standard of north, east, south, west. So this would be north, 30 degrees west. This is called quadrant bearing. The alternative of this is called true bearing, which again, north is always up. And true bearing, the equivalent would be 330 degrees. And unfortunately, angles in standard position start here and spin counterclockwise. True bearing starts at north still, but goes clockwise. So 330 would get me to the same place as north 30 degrees west. Two different ways of communicating the same things. I couldn't tell you when they use each of them. I don't actually really know. I see this one more than this. But sometimes they might say true bearing 330 degrees or something like that. Okay. Any other examples of vectors? How about weight? And what is so a scalar, this is another really important word you're going to come to use a lot, is something we use in vectors all the time, and it's a quantity that has size but no direction. So what would be the associated scalar to weight? Mass. And what would be the associated scalar to velocity? Speed. Like 25 kilometers per hour. Maybe that's the speed limit. It doesn't matter which direction you go. Hopefully not perpendicular to the road. But whether you're going one way on the road or the other way on the road, generally speaking, you have the same speed limit, so I don't know. Okay, or 5 meters or something like that. Okay, so those are examples of scalars. Pretty simple so far. When we do vector diagrams, which we will do some of, I would wonder if any one of you might end up in a program where you end up doing a lot of vector diagrams, or maybe not vector diagrams, but scale diagrams, and vector diagrams sometimes are drawn to scale. We used to do more of this. We don't do as much anymore. Okay, but with vectors, when we're doing a diagram, we use arrows to represent those diagrams. So I might have one vector that's going this direction. And I called that vector A. And I'm going to try to draw the next one about half the length. But I'm just going to eyeball this one. How's that? Not bad. But going a totally different direction. And we're not really doing this until later, but, so this is 2 times this equals this. That statement right there says the length of B is half the length of A. Or A is twice the length of B. We're going to write this down in a minute. So the length of when you're doing a proper vector diagram, the length of the arrow represents the magnitude. So double the length, double the magnitude. And the direction obviously represents the direction of the vector. So these two vectors are just going off in 2 different directions. So some notation. We often use A and B for vectors. We also often use U and V and W. U and V, as I've written here, are just vectors like they've been labeled, like A and B up here. This is how I would denote a vector between 2 vertices or 2 points from A to B. So the direction, it would be starting at A and going to B. So all 3 of these things, they are all Vectors, different ways of writing vectors. Who was it? Was it somebody in this class or somebody who was away who mentioned that Mr. Neal, when he started his lessons, said you're supposed to write a vector like this, but then you never actually did that? Was that you? Did? Yeah. So in math class, we actually do, and it's really important that when you're talking about a vector that you describe it as a vector. So you have to put these accents on top. Just as an aside, this is called a harpoon. So it would be called a right hand or a right facing harpoon. And this is just called an arrow. So a right facing or a right hand arrow. And different people use different ones. We use them interchangeably. It doesn't really matter if a question is worded one way and you use the other symbol. It doesn't matter. The harpoon is faster to draw. So I don't know. That's probably why some people like it. Okay. Stop me if there's any questions, but I'm going to kind of keep trucking forward until we get to some good stuff. This is all just definitions, but you have got to know these definitions so well. Like this is what I'm talking about. You got to start speaking the language of vectors quickly. Okay, so this is called what? Anybody know? Absolute value. It looks like that, and it's related to that, but it's not the same. So interesting that we don't do it this way in physics. This is the magnitude of vector u. So once I put the absolute value symbol around it, I have taken away direction and I'm only talking about the size value or the magnitude of the vector. Okay, and magnitudes, this is why it's related to absolute value, are always positive and scalar. I'm going to talk about a lot of the little tidbits of things that are going to become more clear over the course of this unit. But some operations, when you're working with vectors, result in a vector. We're going to see some of them today. Some operations result in a scalar. It is really important that you have a good grasp of which one is which. When I do this operation, my result will be a scalar. When I do this operation, my result will be a vector. So much of what you do depends on that. Okay? We're going to talk about scalar multiplication today, but I'm going to tell you this. You can't just take two vectors and multiply them together. Vectors don't behave the way integers do. So if you say, oh, I'm going to take this vector and multiply it by that, I'm going to be like, what in the world are you even talking about? And I've seen people do this on tests, and you're like, this person has no clue what they're doing. They said this vector times this vector. That's not even a thing. Okay? So like bed mass, out the window. Bed mass is not a thing when you're working with vectors. Some operations will follow bed mass rules, sort of. Bed mass is not just a thing when you're working with vectors. Okay, you got to know what the result is. You got to know what's allowed and what's not. There's two types of products, we call them, so it's like multiplying. Two different types in vectors. One's called the dot product, one's called the cross product, and they do two totally different things. Okay? And we will learn about them both. And so you don't just take two vectors and multiply them. You say, I need the cross product of these two vectors, or I need the dot product because this is what I'm doing. So that's just a hint of what's coming down the road. Here's an example, or one other thing I wanted to say right here before we move on. I remembered, as an aside, AB, vector AB is not equal to vector BA. Why? Because of direction and so direction is important. Again, as a notation, I think this is intuitive. A lot of what we do today will be intuitive. Some of it won't be. A lot of what we do moving forward will not be intuitive. There's nothing intuitive about it. Seems easy, but not intuitive. But the magnitude of both would be the same. But the magnitude of both would be the same. And we'll get to this. I could say, we're going to write this down later, but like I can put a negative in front of something, that's going to flip the direction, and then they would be equal. So there is a relationship between them, but yeah. Okay, good. So example one is just doing, again, we're going to look at another definition, which is an important definition, and then it gives us a quick little tip of some things that we can do with vectors, but this is not a lot of what we're going to do. This looks like grade 9 material. We're going to move beyond that pretty quickly. Valerie rode her bike 2 kilometers west and 3 kilometers south. We used to do, as I said, we used to do more scale diagrams to this. And if you're doing a scale diagram, you'd have to put on it which way is north, what's your scale, 1 centimeter equals 1 kilometer, whatever. We're not going to do that. But that is something that you could do that another course might ask you to do. I don't know. So I'm going to use my rulers to do this nicely, though, and I'm going to draw it sort of to scale. So 2 kilometers west would be like 1, 2. I'm going to call this A. And then 3 kilometers south. One, two, three. And I'm going to call this B. So there's our vector diagram. We're going to determine just the magnitude of her resultant vector. What do you think the resultant vector is? It's just like the word result. So it is the vector that she resulted in doing. Ignoring the actual path she took, where did she start and where did she end? So there's our first example of adding vectors. My resultant vector, which we generally call R, is A plus B. To find the magnitude, what do you think we're going to do? Yep. Don't have to in this case necessarily, because magnitude ignores value. So the magnitude of the resultant vector R is just the length of R. Pythagorean theorem. It's a right triangle. What if it wasn't a right triangle? You could, but in our case, you probably have, it'll give you an angle, and you could probably just do a non-right triangle trig, sine law or cosine law. Okay, would be probably easier to do than breaking it up into its components, in fact, for us. So in this case, the magnitude of R squared is equal to the magnitude of A squared plus the magnitude of B squared. But see how, like, I'm always calling the vectors vectors, and I'm using magnitude to turn it into a magnitude. Like, this is important notation. We do not get sloppy or lazy about this kind of stuff. So that means the magnitude of R is equal to the square root of 2 squared plus 3 squared, which is 4 plus 9, which is root 13. If you were asked to actually find the resultant vector, not just the magnitude of it, what would you do? You would do SOHCAHTOA to find theta, or if it was non-right triangle, sine law, cosine law. And in this case, it turns out theta equals, depending on the question, but this is something you might do, like, I don't know, in another course or in some, or like in a geography course, maybe you would do this kind of stuff. It turns out theta is about 56 degrees, which means you would call this, but if I was putting it on here, it's 56 degrees here, but that would be 34 degrees south, sorry, south 34 degrees west is what you would actually call that. We're not doing a lot of this, so don't worry about it too much. Don't overthink it. But there are cases where you're asked to find the actual resultant vector. It tends to be just trigonometry and Pythagorean theorem kind of stuff, and you're just solving for lengths and angles and putting them all together. So even though she went west and then went south, her result was root 13 kilometers south 34 degrees west, which is south 34 degrees west. If this is theta, I had to do 90 minus theta to get that one. Yes? No, as a standard, people would figure out what you meant, but as a standard, you always start on the vertical, north or south. Not important for this course. Okay, a bunch more definitions. These, for the most part, are intuitive. Okay. Equivalent. So two vectors are equivalent if and only if, that's what the IFF means, right? You've probably seen that before. Their magnitudes are the same and their directions are the same. That's what we mean by equivalent. Something very interesting about that idea is going to come up in a little bit. Something non-intuitive. In fact, so non-intuitive that some people just cannot wrap their minds around it and just always get it wrong. It seems like the easiest stuff in the world, and it turns out it's not unless you really get it. Okay, we'll talk about it. Opposite. Two vectors are opposite if and only if they have the same magnitude but opposite directions. So, for example, if I call this one U, and I'm just going to eyeball this one, call this one V, U is opposite to V. When two vectors are opposite, one is equal to the negative of the other. Remember, I already mentioned this before when we looked at it. Or V equals negative U. And this is where you say, well, of course, if U is equal to negative V, then V is equal to negative U. And I say, no, that is not always true with vectors. Or, well, this is always true with vectors. But those kinds of intuitions are not always true with vectors. But in this case, it's true. And visually, it makes sense. Visually, it's intuitive, so it would make sense. But there is no inherent positive or negative. To the right does not mean positive. To the left does not mean negative. That being said, integers, if you consider their sign a direction, you could think of an integer as a vector. We'll talk about that a little bit more coming up. But vectors can go in any direction, and integers only go one of two ways along a line. So they're not exactly true vectors per se, but I mean, you could kind of look at them that way. And then parallel, this is an obvious one. Two vectors are parallel if their directions are either the same or opposite, just like parallel lines. But lines don't have direction, but just like you would think about a straight line. Good? That was the first day. Doesn't seem like a lot, right? But it does take time to wrap your head around the definition of vectors and the notation of vectors and that kind of thing. It does take some time. We're going to look at a few different examples of adding vectors. If you're adding vectors that have the same direction, the result will be in the same direction. Nothing weird happens. And the magnitude will just be the sum of the magnitudes. Okay? And if you're finding the resultant vector, you probably need to know the direction and know the magnitude because vectors all have two components. So I'm going to call this A. And I'm going to call this B. But if I take these vectors over here, And there's my resultant vector. So I have added those two vectors. Adding vectors that are parallel but opposite. So remember, opposite means same magnitude, different directions. But they're parallel. Opposite vectors have to be. If the magnitudes are equal, then the resultant vector is, what do you think? Very close. It's a little bit different from 0. It is the 0 vector. I've mentioned this already. When you perform an operation, all the different operations that we're going to look at, some of them result in a vector, some of them result in a scalar. And which one they result in is super important. And adding vectors always results in a vector. The 0 vector has 0 magnitude and no direction, but it is a vector. Some operations can only be done with vectors. So the 0 vector can participate in those operations, whereas 0 as a scalar cannot. So it's a subtle difference, but it's an important difference. Emery, did you have a question? Because by definition, when you add two vectors, you get a vector. So we have to, like by definition, we have to have this thing called the 0 vector that has magnitude of 0 and no direction. It just is. You kind of have to accept it for now, but as you work through it more and more, you'll see why. Otherwise, you're telling me that adding, if I add two vectors and get 0, now I have a scalar. A scalar can't be added to a vector. So all of a sudden, I can't add it to other things. But of course, I could add it to other things. Of course, I could go this way, back this way, and then up that way. Okay, so if this is my u, and this is my v, it's the same magnitude but opposite, then u plus v equals the 0 vector. If the magnitudes, if you're adding vectors that are in the opposite direction and the magnitudes are not equal, this is intuitive. This is like, I know the definition is written down. I don't think you need to memorize this, but the direction will be the direction of the largest vector. And we're going to write this down in a second. The magnitude will be, I'll write it down. The magnitude is the magnitude of vector A minus vector B. Or in other words, the absolute value. It doesn't matter if you do A minus B or B minus A. Because when you take the magnitude, it's positive, so it doesn't matter. This is like integers. 5 plus negative 7 has a value that's negative. And 5 minus 7 is 2. Negative 2, but you take the absolute value of that, right? So if we go back to our example from before, this is A. This is B. Now, my new b, similar to my old b. Then this is r, which is a plus b. And again, it's intuitive. Watch, folks. It's just like you went this way, then you went back that way. So in total, you went that far. Ignoring that, yes, it took more time. Like if you're visualizing somebody walking these paths, sure, it took more time to go there and come back. That doesn't matter. Where did they start? Where did they end up? This is the total distance they traveled. Okay? What about non-parallel vectors? So this is something you've heard of, I believe, in physics. We can add non-parallel vectors by placing the vectors tip to tail. The tip of the tail is connected. The tip of one is connected to the tail of the other. Okay, so I'm going to kind of try to do this marginally accurately here. If you have a ruler, I would encourage you to do the same. Okay, so I've got that to be about just 2 and a bit. And B goes like this. Come on. There we go. Just over 1. So this is what we kind of did before, right, with the example about Valerie on her bike. So the resultant vector is A plus B. And what about subtracting vectors? So this would be the same, like you could go back and apply this to the stuff we did up here, where A plus B, but B was in the opposite direction, was kind of like subtracting B if it was in the same direction. And so there's some overlap here. But what we're actually going to do, what makes the most sense, is treat A, vector A minus vector B as vector A plus the negative of vector B. So again, going all the way back and doing this one more time. So if I take vector, I'm going to do it over here. Take vector A, and then I'm going to do vector B, but I'm going to do it in the opposite direction, still tip to tail. But in this case, we're going the other direction. So I subtracted B. This should be negative B. Because I took that B, which is going this way, and instead I drew it going the other way, but still adding tip to tail. Questions? See, it seems simple so far, right? And I mean, this stuff is, and this is not a lot of what we do, but the idea of vectors and how they exist and what they represent is what we're starting to get the hang of. Okay. Next example. Here's where we get into some interesting ideas. From the diagram, find a single vector that is equivalent to each of the following. These arrows do not stand for direction. What do they stand for? Not quite. Yes, good. So what do we call that? Parallel lines, right? Yeah, good. At the same angle. Parallel lines. These tick marks mean same length. So these two are parallel and these two are parallel. We can denote direction. This is an example where we have vertices that are labeled or points that are labeled. So I can note the direction by saying S to P or P to S. That's how we would do direction with these. So this one's pretty easy, I think. I bet you can do the intuition behind this one. A single vector equivalent to each of the following. If I go from S to T and then I add TR, okay, take vector ST and add TR, what would that be equivalent to? SR, very good. And you can see that because of how this question was arranged, it's kind of like I took the T's and I moved them out of the way. About to blow your mind. Are you ready? This is also equal to vector PQ. And you're going to say, no, it's not. Mr. Blair, you're wrong. PQ is way up there. SR is way down here. This person walked from here to here, so that was where they walked. But here's what I need to say about this. Very important. This is what some people never get their heads around. Vectors do not exist in a position in space. A to B, or in this case, let's say S to T, is a particular one of these edges. But vector ST does not live in that position. Vector ST has a magnitude and a direction, but you can pick it up and put it wherever you want. So because PQ and SR have the same magnitude and the same direction because they're parallel and we went the same direction, they're equivalent vectors. So my answer to this question could be PQ, and that would be totally fine. It could also be negative QP. Because QP goes one way, but I put a negative, which changes the direction, and it could be that as well. SQ plus QR is another easy one. And it's fine in some situations to think about this. Well, I went from S to Q, and then I went from Q to R. So what did I do in total? PQ, or the one that most people would go to would be SR again, but absolutely PQ or QP would all be the same for that as well. Again, because the Q's were in the middle, that makes it easy. One more easy one, ST plus TS. Thank you. Don't just say S, that doesn't make any sense. This is equal to the zero vector. Yep. No, because it's not. TQ is a vector that has length and direction. The zero vector doesn't. Okay, these ones are good to do in steps. We're in particular going to do them in steps because we're going to show some thinking here. So this is a whole bunch of vectors added together, obviously, 4. And the first one's easy because R's are in the middle. And if I go from SR and then I add RT, what's the obvious answer to that question? ST. So we're going to start with that. I took these two, added them together, and I got ST. Because of the way it's formatted, the R's kind of cancel. But what happens now? ST, and I have to add ST. SQ, because ST and TQ are equal magnitude. So if I go that way and then go that vector again, I would be at Q. So I would be at SQ. That is not the opposite of PR, so it's not negative PR. PR is going in a totally different direction. Okay? So this is equal to, now SQ plus QP, adding ST to ST. And then this last one's easy because SQ and plus QP, there's an intuitive one to that SP. You could also call that RQ, right? Everybody okay? What did we say when we said subtracting vectors? It's easier to add the negative. So PT plus negative ST, but how could I write negative ST? That would be better. TS. So you don't necessarily have to do it this way, but like I would say, I would encourage you, if you're stuck or whatever, that this is a very useful thing to be able to do. So PT plus TS just equals PS. This one happened to work out where it was easy. Okay, try the last one. You certainly don't have to show this in 2 steps, so I just went straight to this is PS plus SR plus TP. If you had vectors shown like that, you can't just flip that from PT to TP. There's no way of doing that, right? So this trick only works with these ones. And this first one is easy, PS plus SR. That one's intuitive, so that's going to be PR. But here's where you have to think about picking a vector up and moving it like in your mind. You're going to visualize this. I'm going to actually show it. So if I go from P to R, I've done that. But what is TP? Well, TP is this. But if I pick that up and move it, uh-oh, undo. That would cause damage. If I move it, I can move it wherever I want. So what have I actually done? What's the result of PR plus TP? PT or TR, very good. I could think of, and I could also do this. I could say, actually, I'm just going to write the answer. Whoops. I'm going to write the answer, which is P, let's just go with PT. But you could think of this as PR plus, so from T to P is the same as R to T. So I could rewrite that as RT, and then it's right? Think about equivalent vectors, or if you can move them in your minds. But the important, really important takeaway to this is vectors do not exist in a particular position in space. They do in your minds because you think that person started on that block and they walked to that block. You can't just move that, but vectors in mathematics don't work that way. I'm going to fly through a few definitions here, but they are important definitions, so if you need to come back to them, you can. When A is so that was adding and subtracting vectors, results in a vector. When you multiply a vector by a scalar, so this is called scalar multiplication, the result is the resultant vector, so it is a vector, and we just show it like this, k times vector A. It has a magnitude of the magnitude of k times the magnitude of a, so ignoring all signs. That's like the absolute value of those things. And if k is positive, it has the same direction as a, and if k is negative, less than 0, it has the opposite direction a. That's all intuitive, like multiplying by a negative number or multiplying by a positive. Multiply by a positive, the sign stays the same. Multiply by a negative, you flip the sign. Okay, so that's all intuitive. And note that Ka is parallel to A. Here's an important definition, collinear. This is in your homework, so you need to know this word. When it comes up in your homework, you can come back and refer to it. Collinear is sort of another word we use for parallel in vectors. You actually probably used it back in grade 10. Two lines in grade 10 are either parallel and distinct, which means they're parallel but they're separate lines, or parallel and collinear, which means they lie on top of each other. But we use collinear a little bit more to be the same as parallel. Collinear means they would be on a straight line if we arrange them from tip to tail. And again, this is because parallels don't exist in a particular position. So even if you've drawn them separate, if they have same or opposite direction, they're parallel, they are collinear. Okay? Important definition. If A and B are non-zero vectors, so they both have a magnitude that's not 0, and A and B are parallel, then they are collinear and they are scalar multiples of each other. So I'm just going to hand draw this one. There's A. There's B. So I could say B is, I think, about 2/3 of A, or A is 3/2 of B. So the scalar multiplier there turned out to be a fraction. It could be twice as long, it could be 3 times as long, obviously it could be anything. Still all intuitive, right? So we're good? Again, properties of scalar multiplication. The resultant of scalar multiplication is a vector. Super important. This is not always the case with other operations, but in this case it's true. Distributive property holds. So K times vector A plus vector B is equal to K times vector A plus K times vector B. It's also true that the associative property holds. What is the associative property? This is one you know, but you don't know it by name, possibly. And you can just think about all this, visualize it, and it makes sense. This is the idea that the order in which you multiply doesn't matter. 2 times 3 is 6. 6 times 4 is 24. Or 2 times 3 times 4. 3 times 4 is 12. 2 times 12 is 24. Order doesn't matter when you multiply. So that's normal. That should be normal for us. That will become more important when we find operations that don't satisfy those properties. Okay, very quickly, I'm just going to write this one out. It's obvious. And I can collect like terms just like you did back in grade 9. 2 times vector A minus 3 times vector A is negative vector A, and 2b plus 6b is 8b. Questions? Okay, again, our next example is going to be important. Given the diagram, state 3 equivalent vectors. So there's 3 obvious ones here. So how about we start with FA? And equivalency, we use equals. So equals EB. And direction matters. So if I did CD, I've gone the opposite direction. But I could put a negative in front of it if I wanted to, and then it would still be equivalent. But direction matters. I think we've figured that out by now. This one's kind of a pain. 6 parallel vectors. How about AB and BA? And how about CA? Opposite direction, but still parallel. And those chevrons down there would be DE is also parallel. I think I've kind of made the point here, but we got to do 2 more. FD and EF. And then 2 opposite vectors. How about AB and EF? AB and BA would be the easy one. If that question came up on a test, that would be a fine answer. But just to one final reminder, AB and EF, just because they're separated and they don't look like the same part of the shape, that's not what vectors is about. We got one final question here. Okay?
Would it be like CB or like CA and CB would be like the same?
CA and CB would be the same direction. So they wouldn't be opposite.
Or I mean, sorry, would be.
So if there's just, right, so AB and BA or AC and CB, wouldn't matter which direction you're going. Okay, for the questions below, this is one of the questions in the homework where it gives you a shape like that, and it gives you something like this. So it says vector M is AB, vector N is CD, so vector M is here. Vector N is CD, so it's over here, and the direction matters. And then it also tells us BC is equal to 2AB. So it turns out this length from B to C is twice AB, so what else could I call that? Okay, 2M in terms of M. And the question says, determine each of the following in terms of M and N. So the first few are easy. F to E would be what? M. Because it's the same as AB, so it's M. What about BA? Negative M, because this is like equal to, you don't have to do these in 2 steps, but that's like negative AB, so that's negative M. What about A to C? Three M. And again, you wouldn't have to show this in steps, but this is like A to B plus B to C, which is M plus 2M, which is 3M. Okay, a couple more that are a little bit harder. A to D. Is everybody okay with that? A to D. So 3M will be AC plus N because that takes me down to D. Very good. So this is kind of like AC plus CD. See how I'm breaking it up? This is a useful trick. This looks easy, folks. It's not easy. This is a question that will be on a test, and people get it wrong every year. It looks easy, but it's not. So this was 3M plus N. And what about D to B? Now, whether I go this way and up, or I go up and then left, doesn't matter. But if I want to go from D to B, I got to go backwards along some of these. So this is going to be like what? Close. Not N. Negative N. Very good. Minus 2M. In fact, I'm going to write that out. So this would be like DC plus CB, which is negative n minus 2m. And order doesn't matter, so I could go negative 2m minus n. Distributive property, I could factor that out if for some reason I wanted to. Not really the kind of stuff we worry too much about, but it is stuff that you could do.
That parallel line is so confusing because of the direction, like when you say parallel lines on the picture,
Yeah.
like it says up, that's why.
Yeah. Good point. So the fact that these are pointing up isn't helpful. They make you think about direction, so be careful of that. This is just part of getting used to it. Direction is which one you start with, right? And so n was going that way by definition because it was CT.